Ross Harvey from Hibbing High School. Project I'm presenting as part of my final project is going to be ripping apart and understanding where a 45, 45, 90 degree isosceles right triangle comes from when you take a square and cut it in half, and how its relationships happen when we talk about special right triangles that are needed in geometry and especially later on in trigonometry. So the class that we're going to be dealing with is what we call basic geometry. It is a class full of basically 10th graders, and they are lower level 10th graders. A lot of them are on IEPs. I have a ton of them that are just not very good in mathematical ability, but the state of Minnesota says you have to have a geometry class. So in order to pass and get a state of Minnesota diploma, you have to have a geometry class. So we designed this. It's basically the exact same thing as a college preparatory geometry class would be, with the exception is we don't go into proofs and we don't go quite as far into constructions. We do about half the constructions, but basically not as much proof-based. So this class has a lot of trouble when we get to the special right triangles of 45, 45, 90 and 30, 60, 90. And it comes right off the heels of doing the Pythagorean theorem, which also gives trouble to students. And the main reason why Pythagorean theorem gives them problems is it can be a lot of work if you aren't very good at number sense and you don't understand the square roots and what to do and how to simplify them. So we spent a lot of time with going over that and why this works. And that throws them for a loop. And then we finally apply it to geometry and it gets them throwing for a loop even more. So we have some Pythagorean theorem problems, some ideas about what root 2 is. What is root 2? What's its value? What's it going to do when you multiply by something, when you divide it into something? And then simply moving around the 45, 45, 90 degree right triangle. So I'm going to try and get them so they can best understand why this length right here is x, this is x, and this will always be x root 2, and then of course vice versa if I give them from here to here. So what I've decided to do is I'm going to take my class. I have two classes this year. One of them is very small, 12 kids in it, and the other one is about 25 kids. So I'm going to group them up into groups of 3 and 4. And I'm going to hand each group of 3 and 4 some pieces of paper. They're going to have a square on them. Here's just 3 examples I used. If I have to use more, I'll probably use 7 or 10 by 10 as a square. So what I'm going to do is one group will get this and I'll say solve for x. The other group will get this sheet of paper, solve for x. The other group will get this sheet of paper. And then they're going to come up with as a group, and this won't take them very long, it really won't, because it's coming right off the Pythagorean theorem. So what will happen is that this right here, they'll come up with very easily, they'll isolate that one of these is a right triangle, and I won't even have to prompt them on this. They will see that, they will plug it into the Pythagorean theorem, they should have no problem getting to this, and we're going to go to here and I'm going to ask the answer for 2 ways. I'm going to ask them to give me the simplified square root notation, and I'm also going to ask them to plug it into a calculator because I want them to understand that right here, that 2.828 is longer than 2 is. So I want them to see numerically when you multiply by root 2, it gets bigger. So each group will do that. Then I will take this and my boards will be blank. Each group will give me, I will probably have each group come here and go to half a board and write down their work, and write down their work, write down their work, and then we're going to take a look at it. When we get done with that, I really think at that point, people will come up and understand that whatever this length is, this is the same. They'll see that easily. They should see it's multiplied by root 2. It's going to be very important for them to do that. Then I'm going to put them back in the same groups, and I'm going to hand them squares that look like this. There's just 3 different examples. Again, if I have to make more, I'll just make lots of different ones on sheets of paper. This one, I've given them the length of the diagonal is 3 root 2, 7 root 2, 10 root 2. I'd probably do like a 15 root 2. I actually might even do a 1 by root 2, so that we end up having a 1 by 1 by root 2 on there as well. That will be one of them that we'll talk about. And I will ask them to do the same thing, solve for x. So again, they will probably be able to very easily understand that here's a triangle, there's a right triangle. Right triangle has Pythagorean theorem. X squared plus x squared equals the quantity 3 root 2 squared. They will get to here. I might have to remind them a little bit on this step right here because of course that's going to want to become x to the 4th. This one right here, I may have to prompt them a little bit on it, but once they get to here, they're home free and they'll get to this very easily. I'm also going to have them look at what this is when right before they're done. I want them to each tell me in the calculator what is 3 root 2, what is 7 root 2, what is 10 root 2. Because I want them to understand that this diagonal here is longer than this. So then we will talk about at that point, what's the relationship when you're given this.
how do I get back to this guy? And I want them to understand that you would have to take x and divide it by root 2, and then take x and divide it by root 2, and then after you rationalize it, it comes out to be those nice integral lengths that we got over there. So they will see that 3 root 2 length becomes 3 as a side length. 7 root 2 as the hypotenuse length becomes 7, 10 root 2 becomes 10. They'll recognize how this stuff's all going to work. And I've never tried this before. I'm not really a huge manipulatives kind of a guy, but I think this is going to go pretty well. And I find that this is such a huge thing for them to understand when to multiply and when to divide. And it's mainly down to they just don't have the number sense for it. The ones that understand the number sense, that clearly know that root 2 is 1.4142. Therefore, when you multiply by that, it gets larger. They can really easily see that I got to multiply to get to here, and I have to divide to get to there. So that's what I have got developed for that. I am also going to extend this when it comes time for my final project. We're going to extend this to the 30, 60, 90 degree right triangle and the relationship there, which that brings up a host of other issues on there because of the root 3 relationship and the double relationship, and the double is more than the root 3 is, so you have a lot of things going on there. And then we're going to finish off this particular, the 3 pieces that I wanted to talk about is what happens when you have a right triangle and you have a hypotenuse, an altitude drawn to the hypotenuse of a right triangle, and how to discover what this length is here, what this length is here, what this length is here, and this length, and this length right there, and all those geometric mean relationships. This one is a lot more intensive. It's going to take a couple days to get through. But I'm going to do the same thing. I'm going to bring in manipulatives here, starting with an equilateral triangle cut in half. That develops where this comes from. This one right here, I'm going to have manipulatives with sides that are going to be highlighted in different colors, so then they can put the small triangle, the medium triangle, the big triangle on there. And we're going to one time look at all the different relationships and how the geometric means come into play there, because you have a similar triangle here to this one to that one, so they're all similar to one another. That's a doozy. This one ramps up the difficulty. We start out really nicely by looking at the 45, 45, 90 degree right triangle. So I'm sure most of you guys that teach geometry have done things like this in the past. I'm just not a manipulatives guy, so this is a little bit new to me, but I think this is going to go very well. I started to do things a little bit like this year when I introduced it. I just did it with me leading a discussion with the class instead of them leading a discussion with themselves. So when it comes time to do this, if I have some time at the end of the year, I might retry this maybe the last couple of days of school just to see how it works, but I definitely am going to put this into plan and into action next year with these 10th grade basic geometry level students.